Alright, it's a few more seconds. Stop at 38. Okay, E is the right answer. Remember, Coulomb's law here, guys, is K Q over R squared. This is equal to our force. So if I increase this distance by a factor of 3, then that decreases the force by a factor of a ninth, because it's an inverse square relationship. Two balls plus Q plus 4Q separated by 3R. Is it possible to place a charge Q naught between these two charges so that the force on that charge is 0? And if it is possible, then what is the sign of Q naught? Is it positive, negative, it doesn't matter, or it can never be 0? That is, if I place a charge right here in the middle, what must be the sign to get 0 force on it? Think about how the vectors are, what they look like. I'm going to stop at 115. Alright, let's see, we're sort of split here. Let's take a look and see. So if I put a negative charge somewhere, let's just forget about the magnitudes of the charges, but if I put a negative Q right here, the force due to this charge would be in that direction, and the force due to this charge would be in that direction. All right, so that could give us a 0 charge. Well, let's imagine instead that I have a positive charge there, positive Q, then the force due to this charge would be in this direction, and the force due to this charge would be in that direction. So could I get a 0 force with that scenario, with a positive Q? Right, so what's the right answer then? Right, C is the right answer. Let me ask you another question. There's a particular place here where the force is going to be 0. Is that place where the force is 0, is it in this region? I'll call this A. Is it right in the middle? I'll call that B. Or is it over here? I'll call that C. That is, where would you place this positive or negative charge Q naught such that the force would be 0? Would you place it to the left of the middle, right in the middle, equidistant between the two charges, or to the right of the middle? Left, middle, or right? Where would you place it? In which of those regions? In order to get a force that's equal to 0. Come pretty well on this. I'm going to stop at 45. All right, very good. A is right. You want to get as far away, you want to get further away from the plus 4Q part, right? Because then that will diminish the force. So if I draw my charge, say I have a plus Q charge right here, I feel a force due to this charge in this direction, and I can feel a force that has an equal magnitude in the opposite direction. Even though it's a bigger charge that it's interacting with, that plus 4Q charge, if I'm further away from it, then it will diminish the force. So that there is a point in that region A where the force is 0. Proton and electron are held a distance of 1 meter and then released. As they approach each other, what happens to the force between them? Does it get bigger, smaller, or stay the same? The force between this proton and electron. I'll stop at 45. Very good. As they get closer, the force gets bigger. They're held apart, distance 1 meter, and then released. Which particle has the larger acceleration? We know they have the same force at all times because of Newton's third law, but which particle has the larger acceleration? Ours is the same. Just a few more seconds. So most of you have the wrong answer right now. Let me help you out a little bit. Proton and electron are different. How are they different? Their masses, they are a lot different, right? So a proton is much more massive than an electron. It's like 10,000 times more massive than an electron. So how does that affect the acceleration then? If the proton is a lot more massive, how does it affect the acceleration? All right. I'll stop at 110, yeah. 110. Still missing somebody out there. There we go. That's pretty good. The less massive object, it has less inertia, so it accelerates more quickly. F equals ma, right? If m is small, a is big. They both have the same force, but the electron is a lot lighter, and so it accelerates much more quickly. All right, where would they meet? Same scenario, I'll let them go. Where would they meet? In the middle, closer to the electron, or closer to the proton? All right, just a few more seconds. I'm going to stop at 35. Excellent.
Oh, the first joke of the semester.
I haven't told y'all a joke yet?
No, man.
I didn't tell you the turtle joke?
What?
The turtle joke? Oh, yeah, I'm sorry. I thought I told you already. What did the snail say when he's on the turtle's back?
Whee!
That was lame for the first one, huh? Because the turtle goes a lot faster than the snail? Get it? All right. Forces. Which of the arrow best represents the direction of the net force on the charge plus Q due to the other two charges? Let one be A, two be B, three be C. A few more seconds. Let's stop at 45. Very good. B is the right answer. You want to draw your vectors here. So I have a vector due to the plus 2q charge that's in this direction, and the plus 4q charge that's twice as big because it's a bigger charge. And since this vector is twice as big, the resultant is closer to it when you add up those vectors. Okay, we'll come back to this. We're going to get into electric fields now. We'll come back to this on Monday. And maybe even finish up the chapter on Monday, the chapter 1 on electric fields. So as of now, if you really want to do stuff, you could work through the first homework problems on forces and fields. On forces. And then you might go look at the field stuff too by the time we're done. Alright? So if y'all are looking for physics to do this weekend. And then of course there's the chapter 0 homework, the gravitation homework, which will be on the exam 1 week from Monday. Just to give y'all a flavor, let's see, I think everybody's had me except for Gary. There's somebody else in this class, right? Patrick or somebody? Oh, that's my other class. But anyway, there are old exams online. The exam will be 15 multiple choice plus 4 to 6 free response. A lot like the homework. In some cases, concept tests, these multiple choice questions will be like the multiple choice part of the exam, largely conceptual, no calculations. I give partial credit, so it's good for you to give answers. Take it in here, yeah, it's a week from Monday. I allow the students to come in like 15 minutes early to have a little extra time. All right? More about that next week. All right, let's look at electric fields. So we're talking about gravitational fields, and electric fields are going to be very similar. Remember with gravitational fields, when we were talking about that, our gravitational field is really just another word for G. So we call G gravitational acceleration, but we can also call it the gravitational field. And that gravitational field is some force per unit mass. And in a similar way, our electric field will be a force per unit charge. So we can express our gravitational field as newtons per kilogram, and we'll see that we can express our electric field in a very similar way. So these are very similar forces in the way that they respond. They're both inverse square forces, inverse square law forces, that 1 over r squared dependence. So they're very similar and they work a lot the same. So the electric field exists in the space surrounding a charged object. We're going to define our electric field. It's a vector quantity, just like our gravitational field. We define it as the electric force over Q naught. So this is a definition. That's what the 3 lines mean, is it's defined as. It's defined as our force per our unit charge. And here we're going to call Q naught is a positive test charge. Also, this is an imaginary charge. In fact, I had a high school physics teacher, and she always said that, Miss Carey, she always said that she carried 2 things in her back pocket. You know what she carried in her back pocket? All the time. She carried her right hand, for the right hand rule, and then she also carried a positive test charge. So it's useful to just always have this imaginary positive test charge for reasons you'll see in a bit. It allows you to find the direction of the electric field and just to think about the electric field, because we use this imaginary positive test charge to find the direction of the electric field and think about its magnitude as well. All right, can you imagine your imaginary positive test charge in your head?
I'm still imagining her walking around with the right hand.
Yeah. She didn't always keep it back there. Sometimes she used it. All right, so the units of the electric field are newtons per coulomb. All right, but I'm going to go ahead and also express this in a different term. You can write this if you want. You don't have to. I'm going to put it in a little thought bubble. The units are also volts per meter. Volts per meter. We'll see that when we get into potential. Volts is a measure of potential. So when we're talking about electricity, we have forces, electric fields, and electric potential. The forces are just, our forces. The electric field is a force per unit charge, and the potential is a energy per unit charge. So those 3 quantities are all related. And later when we get into potential in chapter 2, we'll talk about potential and how it's related to the electric field. So I'm just going to sort of throw that out there right now. Don't write it down if it confuses you, but you'll see it again in chapter 2. All right, when a charge Q is within an electric field, the force the charge feels is given by this. Just by that definition on how we define the electric field, if I have a charge that's sitting inside of an electric field of some magnitude, then that charge will feel a force like that. And that just comes about from how we define what is the electric field. So with that, let's try this quick test. A proton is accelerated from rest in an electric field of 100 volts per meter what is the velocity of the proton after 2 seconds? I'm just trying to remind you your kinematics equations that we had last semester. You won't have terribly complicated kinematics problems. They'll be simple one-step problems as they're related to electric field. Actually, there's some in your homework. So here I want to know what is the velocity of this proton after 2 seconds. I'm going to give you the mass of the proton there. And of course you know the charge of a proton, right? It's the fundamental unit of charge. So the charge of a proton is equal to 1.6 times 10 to the minus 19 coulombs. That's on your equation sheet. The fundamental unit of charge is on your equation sheet. Go ahead and try that on your own. A couple steps you're going to do. First, you're going to find the force. Then you'll need to find the acceleration, and then you can find the velocity. So it's three separate steps. Find the force, the acceleration, and then the velocity. Don't forget you can ask your neighbor what they put. Compare your answers. And also notice here, I've listed the units of my electric field as volts per meter. It's not newtons per coulomb, but that's the same. All right, about 20 more seconds or so. Just 10 more seconds. Just guess if you're not sure. And stop at 5:20. I think B is right. I'm going to come back. I'm pretty sure it is. So first I want to find my force. F equals QE. That's going to be 1.6 times 10 minus 19 times E, which was 100 newtons per coulomb. It's in coulombs. And so that's 1.6 times 10 to the minus 17 newtons. And then I want to find my acceleration. So A is going to be equal to F over M. So that's 1.6 times 10 to the minus 17 divided by the mass, 1.67 times 10 to the minus, what is it, 27? All right, so that's roughly 10 to the 10th. And then my velocity is what's that? Oh, but that's roughly 10 to the 10th. Yeah, because it's 10 times 10 to the 9th, which is 10 to the 10th. Right, I just rounded up. Because if I look at this, like, these basically cancel out. And it's 10 to the minus 17 or 10 minus 27. I'm sorry, I'll put a little squiggly line there. All right, so my velocity is 2 seconds, or excuse me, is A times T, which is 2 times 10 to the 10th, which is B is the right answer. I rounded off there, but yeah, you're right. Okay. All right. Pretty straightforward? Yeah. You'll see some homework questions with sort of basic kinematic stuff like that. All right, let's look at how we calculate the electric field. Electric fields are used for lots of purposes, and they're also used a lot in just talking about how atoms interact with one another. So it's useful to be able to calculate what is the electric field. Remember Coulomb's law. It can give us the force between a charge and this positive test charge, Q naught, this imaginary positive test charge. And let's say I want to know what is the electric field due to this charge. First, I imagine this force between my imaginary positive test charge and whatever the charge is that I want to find the electric field from. So let's say that I have this charge Q here, and I want to know the electric field at some point out in space, some distance from that charge Q. I imagine my positive test charge Q naught being there, and I ask myself, what would the force be? But I also know that the electric field is defined as F over Q, in particular F over Q naught. So my electric field at this point is defined as this quotient of the force that Q naught would feel at that point, divided by Q naught. So then it's pretty simple to get an expression for the electric field. It's going to be that force from Coulomb's law divided by that imaginary test charge. And so that imaginary test charge cancels out, which is a good thing, right? Because it's imaginary. It doesn't really have a value. So if you're ever hard pressed to put in a value for that imaginary test charge, you couldn't do it because it doesn't actually exist. And so my electric field then has a magnitude of KQ over R squared. All right, so far we have two expressions. We have Coulomb's law, and then we have the electric field. And then later we actually get another expression for potential, which is sort of the third part of this, this what's it called, a triumvirate. You have three things. Anyway, so we have our Coulomb's law, and now we're going to have our electric field. Electric field is a lot like Coulomb's law. It's a vector quantity, just like your forces, and it's calculated in much the same way. All right. So the electric field is not dependent upon the test charge. That test charge went away. And so the E field, or excuse me, the test charge rather, is only a tool to sample and define the electric field. We'll use it more particularly to find the direction of the electric field. Just a bit. All right. Can I go down? Okay, I'll second. I tell you, my kid got first place in the social studies fair. I did tell you that. He worked really hard.
Did he get first place this time?
He didn't do science fair. He didn't want to do it. He likes history. He's big into history, which is a little disconcerting for me and my wife because, like, I love history. Like, history is great. I understand the need for historians and people to study history, but I don't think it's real practical. Like, it's hard to get a job in history. Am I right about that? But, I mean, most of y'all, you'll go out and graduate, and you're going to be making $60,000-$70,000 to start, right, as chemists or engineers or whatever. But a historian, $25,000. Nothing wrong with making $25,000 a year, but you're going to be scraping by your whole life.
What do you think we should be?
Huh?
What do you think we should be?
I don't know, a plumber or something. Plumber, that's... No, I don't know. Whatever he wants to be is fine. Okay. Chemist would be good. Chemist is a good job, I think. Don't y'all think? Chemist is a good job.
We would have to take organic.
Yeah, organic is useless anyway, right? Okay, so the sign of the charge Q determines the direction of the electric field. So we're going to use this test charge Q to find the electric field. The direction of the electric field is the same direction of the force felt by our positive test charge. So for example, if I have a charge here, and I want to know the direction of the electric field at this point, I imagine my positive test charge, which is imaginary, but it has a positive charge, and I ask myself, what is the direction of the force on this charge? What is the direction of the force, left or right? It's to the right, right, because it's repelled from that positive charge. So my force, due to this positive test charge, is in this direction. And it turns out also, because of the way we define the electric field, that the electric field is in the same direction. Field lines are sometimes called lines of force. Did we give you that term last time when we did gravitation? I'll show you in just a bit. I think I did. Yeah, so field lines are very similar to the direction of a force. They're defined by the force. Similarly, if I had a negative charge, then the force would be in this direction, and so the electric field would also be in the same direction. So the electric field is in the same direction of the force that a positive charge would find. And so anytime you want to know the direction of the electric field, you pull out your positive test charge and you ask yourself, what is the direction of the force that this charge will feel? And then that'll tell you the direction of the electric field. It's kind of like with the gravitational field. We have a mass, and we ask, what is the direction of the gravitational force on this mass? And then that's the direction of the field line, the gravitational field. But with mass, it's always towards the object, because gravitation is always attractive, never repulsive. Okay. Similarly, as we did with gravitation, we can use the superposition principle. We're not going to go through all the vector addition. We've already done that twice, I think, actually. With gravitation and with electric forces, but I'll sort of just get it set up. Let's imagine here I have Q naught, and I want to know what is the electric field at a point where that positive test charge is. The electric field due to charge number 1 will be in that direction, and the electric field due to charge number 2 will be in that direction. Because those are the directions that the forces would feel, or that the forces would be. This charge would be repelled from this charge, so the field is in that direction due to this charge. This charge would be repelled from that charge, so the electric field is in that direction. Follow that? Sort of? We're going to do some examples. Josh?
I don't mean to ask a dumb question really. So like the Q naught is just basically like an imaginary positive thing there.
Mm-hmm. Right.
That's all you have to do. Like it's not actually there. You're just kind of like
Right. Yeah, in fact, we're just going to get rid of it now. I'm not going to draw it anymore.
Okay.
So it's an imaginary charge. It doesn't exist. We use that imaginary charge to define the electric field, and so in that way it's just a tool. It's not actually there. It doesn't have a value. You can never ascribe a value to it. But you know it's positive. All right, so yeah, we're going to stop drawing it, and then if I draw the electric field, here I have E2 and E1. And then if I want to know the net electric field, I just add them up. So the sum, my net E field, is equal to E1 minus E2. Or rather, it's the magnitude of E1 minus the magnitude of E2. Just like we did for vectors before. You just subtract the two. One's positive and one's negative. And then the charges are identical, Q1 and Q2. Then at this point, equidistant between the two charges, the electric field is equal to what?
0.
Right. If those are identical and you're at a point equidistant, then the electric field is 0. So if I were to place a charge here, it would feel no force at all, irregardless of what the magnitude of that charge is, of course. Okay, you can also have charges that are distributed in 2 or 3 dimensions. We'll just do 2-dimensional charges, like we did with Coulomb's law. I'm going to do an example. I'm just going to set it up, though. We're not going to go through all the vector addition and subtraction. Can I go down? Okay. All right. So say, for example, I have these 2 charges. I have a minus 2 nanocoulomb and a plus 3 nanocoulomb, and I want to know what is the electric field at this location. I imagine my positive test charge there, and then I just sketch in my vectors. So my field vector E2 will be in this direction. My field vector E1 will be in this direction. All right, the reason being, a positive charge would be attracted to this charge, a positive charge would be repelled from this charge. So I draw my E field vectors like that. Then, of course, I need to find my angle. Recognize that this is a triangle. This angle, as we've done before, is 37 degrees. So this angle is 37 degrees. And then we go about the task of calculating the magnitude of E1, which is going to be KQ1 over R squared. E2 is KQ2 over R squared. I'm going to call these R1 and R2 because their distances are different. Calculate the magnitude. Then you find the X and Y components of E1. I'm not going to write anymore. Add those X components, add the Y components, although in this case there's only one Y component, and then find the resultant magnitude of those 2 vectors. Just like we did for gravitation and just like we did for Coulomb's law. It's a vector addition problem behind it. You're good with that? You definitely have a 2D vector addition problem on the test. Absolutely, no doubt. It'll either be gravitation, forces, or fields, but this is the 3rd time we've seen it, so it'll certainly be on the test. All right? That's exciting, right? Because it should be easy. Easy 15 points. 10, 15 points. All right. If you want to go through that, you can go through it here. I'm not going to go through it, though. Let's try this little quick test. Here I have a collection of charges, a plus 2Q and a minus 4Q charge. And I want to know where is the electric field the greatest in magnitude. Is it at a point A, which is equidistant between these 2 charges? These 2 charges are separated by a distance B, and this point A is halfway in between. Or is it a distance at a point B, a distance D over 2 from that minus 4Q charge? Where is the electric field the greatest? At point A, B, do they have the same magnitude, Or does it depend upon that distance that we assume? So you can't know. Right now, you're about split half and half between a right and a wrong answer. So, a very helpful thing is to draw your vectors and see how they add up. All right, just a few more seconds. Let me think first. I can't think. I'm sorry. I'm gonna stop. Sorry, I can't think of it. I'm sorry. Huh?
On Monday.
On Monday, right. All right, but A is right. So a good way to do this is just draw the vector. So my electric field at this point, due to this charge, is going to be in this direction. And my electric field due to this charge is going to be half that of what it was, but it's going to be in that direction. It's going to be half because the charge is half, right? And then over here, the electric field due to the minus 4q is going to be in this direction, right? And it's actually going to be the same magnitude as this because it's the same distance away. But then the electric field due to this charge, it's going to be smaller than it was here, but it's going to be in this direction. All right, so this vector added with this vector is bigger than this vector minus this vector. Because the green is the same distance, is the same length. The reds are different, but the green is the same. So A is the right answer. All right. We're going to get into some derivations. I'm just going to sort of preface it right now and then let you know what you'll be responsible for on the exam. But we can often we'll have particular configurations of charges. Y'all might do this in PChem. You do a dipole, electric field of a dipole. You must deal with dipoles a lot in PChem, is that right? We all just really started. Yeah, I think you will deal with dipoles because, you know, a lot of atoms are dipoles where you have one charge and another charge. So let's say that, and so we'll deal with configurations of charges and figure out what is the electric field due to those configurations of charges. So for example, let's say that we had a charged ring and we wanted to know the electric field in the middle of it. So if I want to know the electric field at this point, what I would do is I would break up this ring into little differential elements. Each of these elements would have a charge dq, and as a result, each little element would have an electric field dE. And then I would sum up all those differential elements of the electric field. I would say dE is equal to K dQ over R squared. I would sum them up and do an integral, integrate over that surface, over that shape, and find what is the net electric field. Now in this case, it's easy. What is the net electric field at this point due to this ring of charge? is 0 because of our symmetry. I know we're almost out of time, but because of our symmetry, I get vectors that all go in these directions. And so that adds up to a net electric field of 0. All right, so we're going to look, though, at the electric fields of different configurations of charges. We have 3 in your book, but you're only going to have, I'm only going to go over 1 in class, and one of the other 2 I want you to choose to do as like a pre-test kind of thing. How we've done derivations in the past, where you do the derivation before the test and you bring it in on the day of the test, and you'll give it to me, and that'll be one of your questions. So you can use any resource you can work together for the first test, yeah. So we're going to do one of these derivations. We're not going to do the dipole. So if you choose to do the dipole, a little hint is you'll need the binomial theorem. Huh? Yeah, it's in the book. Yeah, so you'll need the binomial theorem. Oh yeah, there it is right there. We're not going to do that one in class. We're going to do the charged ring in class. Okay? So you can either do the dipole or you can do the charged disk. And I just want you to express the electric field in terms of Z, R, and alpha for the charged disk, or in terms of Q, D, and Z. Basically, you're going to get this page on your, or you're going to turn in this page. Maybe I'll send out this page to y'all so you can just fill it in. You'll have the figure and all that. Okay, that'll be for your test. It's probably worth 10-ish points. All right. You can use any resource you want. Books, internet. They're on the derivations are on the internet. More about that next week. But I also want a few sentence description of how you did it, just like we've done in the past with derivations. All right, I'll see y'all. Y'all have a good weekend. I'll study all weekend.